Hi guys, this is the video for 441, and so we're going to learn about a theorem called L'Hopital's rule, and yes, that is how it is said, L'Hopital, and basically this is a way we can find limits if a limit produces an indeterminate form. So we did this actually back in chapter 1, but we had some other strategies for finding the limit. This time we're going to be able to use derivatives to help us find the limit of functions that have indeterminate forms. So indeterminate forms will happen when I get 0 over 0 or infinity over infinity. So first we just need to be able to identify which type. If it is not one of these types, I cannot use L'Hopital's rule. So first we just want to make sure we can identify if we do get an indeterminate form. So let's look at this first one. So I'm going to look at the limit as x goes to 0 of cosine of 3x minus 1. So that's just the numerator. And then I'm going to look at the limit as x approaches 0 of 2x, the denominator. So if I substitute in 0 here, I would get cosine of 0, which is 1. 1 minus 1 is 0. If I plug in 0 here, I also get 0. So this does produces, so this would be yes, determine whether it produces an indeterminate 4, and it produces this one, 0 over 0. Okay, this one we're looking at as the limit approaches 1. So if I look at the numerator, 1 minus 1 would be 0. If I substitute in 1 here, I've got 1 plus 2 is 3. 3 minus 3 is 0. So this one is another yes, 0 over 0. This one, if I substitute in 3, I would get 9 minus 2. This would produce 7 over 0, so that is not an indeterminate form. Yes, I'd have to come up with something else to find the limit, but this is not an indeterminate form. This would not be one I could use L'Hopital's rule on, so we're just going to say no there. Here, we're looking as x approaches infinity, so as I go to infinity, I put really, really big numbers in here and square them. It's also going to infinity. Same with this one. If I put any really big numbers in for x, for e to the x, it's also getting really big very fast. So this is, yes, it's producing infinity over infinity. Okay, so now let's look at, okay, well, how do I use this theorem then to find limits of these kinds of functions? So what L'Hopital's rule says is that we can actually find the limit by taking the derivative of both the numerator and the denominator and then using direct substitution. So, in other words, the limit, if we get an indeterminate form of 0 over 0 or infinity over infinity, L'Hopital's rule states that the limit of the quotient equals the limit of the quotient of their derivatives. Okay, let's test it out. All right, so here's kind of our steps. First, we need to check, does it produce an indeterminate form? If not, we're not going to use L'Hopital's rule. So first, we have to do that. Okay, so we are going to look at these separately. This is kind of important for AP notation, okay? So we're going to look at these two derivatives. So we're going to show, okay, the limit as x approaches 0 for tangent of x. So if I put in 0 into tangent, I get 0, okay? And I'm going to separately look at the limit as x goes to 0 of 6x. Same thing as if I substitute 0 in there, I also get 0. So we never want to say equals 0 over 0. This is no, 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 don't do that, okay? So we never want to say that. We will say this produces an indeterminate form of 0 over 0. Okay, so this statement's going to be really important. Okay, don't write equals 0, 0. Say we get an indeterminate form of 0, 0. Okay, so then we can apply L'Hopital's rule. So it says differentiate f and g separately. So kind of how we want this to look is I'm going to say the limit as x goes to 0. I'm going to show that that's what I'm doing. So I'm taking the derivative with respect to x. So I'm going to write d dx on both the numerator and the denominator because we're doing them separately. So I'm finding what is the derivative of tangent of x and what is the derivative of 6x. Okay, so let's go ahead and do that. So the derivative of, and we're still keeping our limit notation until we do direct substitution, derivative of tangent is secant squared, okay, over derivative of 6x is 6. Okay, so now if I substitute in 0, let's see, we get 1 over 1 there. So remember, secant squared is 1 over cosine squared, right? This is 1 over cosine squared. So if I plug in 0 there, I get 1. 1 squared is 1. 1 over 1 is 1. So this one is going to produce 1/6. Okay, so there is our limit. Okay. All right, let's try this one. This one I'm going to infinity. So once I put really, really big numbers into natural log, it's going to infinity, going to infinity. So this would be, we could say this produces an indeterminate form infinity over infinity. Okay, so we're going to apply L'Hopital's rule. So the limit as x goes to infinity, again, I'm going to write out what I'm doing. I'm taking the derivative with respect to x of the numerator, and I'm taking the derivative with respect to x of the denominator. So I'm showing what I'm doing, and then I'm going to say what that equals, keeping our limit notation, because we haven't substituted anything yet. Derivative of natural log of x is 1 over x. Derivative of x is 1. So we get this equals 1 over x. If I were to plug in very large numbers here, 1 divided by something very, very big goes to 0. All right. Next one, also going to infinity. You can hopefully see this one's also going to produce an indeterminate form of infinity over infinity. Produces an indeterminate form. Okay, so we are going to take the derivative. So the limit as x goes to infinity, we're taking the derivative with respect to x of e to x, and the derivative of our denominator, x. Okay, well, what does that equal? The limit as x goes to infinity of the derivative of e to the x is itself. Derivative of x is 1. So now when I think about putting infinity in there, putting really, really large numbers in there, e to the x still goes to infinity, but it's no longer infinity over infinity. It's infinity over 1, so my limit is infinite. I think that is it. Yep, that's the last one for this video, guys. Thanks for watching.